Hi, David Kessler from Cosmos Cluster 3. I'm going to do my scientist mathematician presentation first, and my scientist is Copernicus. So, just waiting for it to get started here. There we go. For his schooling, his father died while he was still fairly young, and then he was raised by his uncle. And he went to school in he kind of moved around a bit, but where he learned most was at St. John's School. A lot of his learning was from books he read. So he read from Euclid, Hale Abernagel, and as he read all these books, he collected them and eventually ended up having a very large library and collection of books. Okay, so early on, he kind of noticed there were some contradictions in the theory of how the planets were set up, and the current, some of the current relevant theories were Aristotle's theory of homocentric spheres and Ptolemy's mechanism of eccentrics and epicircles. His theory was the heliocentric theory. At this point, it's still in its early stages, but he had the idea that the Earth sort of moved on three axes of motion, and he began to develop it more over time. However, he did not release it to the public at first, as he was worried that the public would sort of scorn him and they wouldn't like his novel and incomprehensible new ideas about the universe.
He was afraid. He was afraid from the church.
Soon though he got a pupil, George Joachim Redicus. Yes, it does not have an E, that is actually how it's spelled, I didn't make a typo. And he began to pressure Copernicus a lot to release his ideas. Soon he finally decided to print his ideas in a book. De Revolutionibus Orbium Coalescium was what it's called. And his pupil was there while he was printing, but then left this guy, Andreas Osiander, in charge, and he kind of just added some stuff in, which wasn't really supposed to be there. There were 6 parts to his theory. The sort of general vision theoretical part had some parts about the motions of the sun, the motion of the moon, and the longitude of non-terrestrial motion, and the latitude also. For his theory to work, he made some assumptions, such as the Earth is not the center of the universe, actually, as was believed a lot at the time. The Earth has more than one motion, and the planets actually rotate around the sun rather than around the Earth. Next, I have Euclid, my mathematician. The reason I went with white just seemed less distracting to me, if you were all wondering. There's more pictures later on also. Alright, so Euclid is often known as the father of geometry. His main sort of works were his Elements, which is a series of books which he discussed many mathematical topics. And then it used a logically coherent framework, and even though there was actually no listed author on the Elements, but from a sort of a commentary on the Elements at the time, which listed Euclid as the author, they were able to figure out that he wrote the Elements. Okay, so books 1 through 4 and book 6 have to do with plane geometry. Books 5 and books 7 through 10 have to do with number theory, and books 11 through 13 have to do with solid geometry. Okay, so at the time, in the books it's really only referred to as just geometry, when in Elements, what it really means is Euclidean geometry. At the time, they didn't even believe there was anything possible other than Euclidean geometry. So what it used was an axiomatic system where it used a bunch of simple things to start out with and built with those to more complicated things like theorems. Okay, this is one of his things that a lot of people found confusing at the time. It's less obvious. It says that if there's 2 lines and a line in between them, and both these angles are acute, eventually these 2 lines here will intersect if they go on indefinitely. So how he measured things, he used measures of distance and angle, and what he did for measuring his angles is he based everything off a right angle. So like a 45-degree angle, he would call like a half right angle, and like that. Alright, here's some important results. It was that if it's an isosceles triangle, A would be equal to B, and C would be equal to D. And also the triangle angle sum theorem, where it all adds up to 180. It helped lead to the Pythagorean theorem. And Thales theorem, which is if you have the diameter of a circle, and then these points out here, this angle right here will be a right angle. Alright, on to my topic now, boundary layers and viscous interactions. Also by me, David Kessler. Alright, so the boundary layer is the layer of fluid around an object where the effects of viscosity are still like sort of present in the flow around it. So, Brantel was sort of one of the first people to come up with the aeronautical boundary layers, and what these boundary layers were able to do is they're able to greatly simplify equations of fluid flow, which were fairly complicated at the time. So how it simplified is it sort of split it into two areas where there's one inside boundary layer where things act very differently than the one outside, and it makes the calculations easier. So the inside area, the effects of viscosity are stronger. Pretty much all the heat transfer is in the inside layer for the boundary layer, and most of the drag is also from the inside layer. The outside layer, there's much less viscosity and it's fairly negligible. Here's kind of a picture to help see how the flow would go around an object like the wing of a Alright, so the thickness of the velocity or layer is the distance from the solid body where the viscous flow velocity is 99% of the free stream velocity. Then, similar to that, we also have the heat layer, which is the distance from the solid body where the temperature is 99% of where it would be in the non-viscous flow temperature. And you can tell what the relationship, the ratio between these two is using the Brantel number. If the number is less than 1, the heat one is larger. If it's greater than 1, the velocity one layer is larger. And if it is equal to 1, they're the same. Okay, so what it's used for, it's used in gliders, commercial planes a lot, and you're able to use it to see how the effects of pressure and drag and friction drag on objects. Okay, so with Reynolds number, it's fairly easy to maintain a streamlined flow on an object with a low Reynolds number. But if you have a higher number, the boundary layer thickens and it's harder to maintain a streamlined flow. However, with a low Reynolds number, there's still some issues. Poor pressure gradients greatly affect it, which can lead to more pressure drag, which even though you'll have less friction drag, you'll overall have still greater drag. Some solutions to low Reynolds number, you can add a turbulator, which adds some turbulence around the layer, which will stop the boundary layer from separating from the wing of the object. Oh, whoops, I was supposed to say golf balls. Pretend that's an F. And it's used on golf balls. With the little divot. Okay. Higher Reynolds number, which is how it is on like commercial airplanes and that sort of thing. One solution is you can suck away the boundary layer, but that doesn't really work too well, too complicated. You can use natural laminar flow techniques, which works better to reshape the aerofoil or fuselage. Hydrodynamics also kind of works the same way with the boundary layer. It's for ships and submarines, but unlike air, water does not change in density greatly. So, okay, the equations they had before boundary layer were sort of a thing, were the Navier-Stokes equations, where U and V are velocity components. I think that's rho is density, P is the pressure, V is the kinematic velocity, the viscosity. Alright, so here are the new boundary layer equations. They're much easier to use than the old Navier-Stokes equations and allowed improvements in the field at the time. sometimes we'll end up with a turbulent boundary layer, which makes things much more complicated. However, you can get around this using a mathematical technique known as the Reynolds decomposition technique. And what you do is you, heat transfer, it's only affected by velocity values close to the surface of the object where the interaction is occurring. And for, if you have a large Prandtl number, the interaction will be very close to the surface of the object. All right, that's my presentation. Thanks for listening.